Hello everyone, I'm Lingming Zhang from Zhejiang University. Today I will introduce Waltzz, our domain-specific fuzzer for WebAssembly runtimes. Let's start with some background. WebAssembly, or Wasm, is a high-performance binary instruction format that provides a way to run code written in different programming languages on the web and other platforms. And the Wasm runtimes act as memory-safe execution environments for Wasm modules, which, when compromised, can lead to severe outcomes such as remote code execution and sandbox escape, as shown in these previous attacks. Therefore, we try to leverage fuzzing to promptly identify security bugs in Wasm runtimes. However, we find inherent limitations of current fuzzers when applied to Wasm. Traditional mutational fuzzers like AFL++ predominantly operate at the byte level. For Wasm, this quickly hits the wall. Wasm is a stack-based language where instructions push and pop stack values of specific types. Wasm runtimes are demanded to validate the correctness of Wasm stack semantics of input modules, allowing only valid modules to be executed. For example, the runtime ensures that an i32.add instruction is preceded with instructions that push two values of i32 type. However, a simple bit flip performed by AFL++ may change the opcode interpretation and alter the stack semantics from pushing a value of i32 type to a value of i64 type, resulting in immediate rejection. Our preliminary experiments show that over 98% of AFL++ generated test cases are invalid, hindering its performance. On the other hand, generative fuzzers like Wasm-Smith ensure validity by design, but they struggle with exploring diverse instruction combinations comprehensively because of their reliance on fixed and predefined rules and the vast input space, where there are over 400 instructions in current Wasm standard featuring varied purposes. Thus, our core challenge is to devise a Wasm runtime fuzzer capable of generating diverse and semantically valid inputs. And to address the validity issues with the generated test cases, we take inspiration from previous works such as Code Alchemist and Vasily, which leverage the type system to ensure semantic correctness. Similarly, the basic intuition here is that when analyzing a sequence of Wasm instructions, we can disregard the specific operations performed on the stack values, and instead concentrate solely on the accumulative effects on the stack types, as this is the primary aspects checked by Wasm runtimes. Therefore, we propose stack-invariant transformation, where one instruction sequence can be interchanged with another if their impacts on stack types are compatible, thereby maintaining the invariant state of the stack. For instance, the code snippet 1 and 2 can replace each other since they both pop no values and push one value of i64 type. Taking stack-invariant transformation as the core guiding principle, we have devised several mutators and generator, which tackles the diversity issues, and this will be discussed later. Here, we first introduce the workflow of Waltzz. At a high level, Waltzz takes an instrumented Wasm runtime, a collection of Wasm seed files, and optionally a test harness as inputs, and outputs the bugs identified within the runtime. Starting with a seed input, Waltzz passes it to construct its typed intermediate representation, or IR. The typed IR then undergoes a series of stack-invariant mutations and generations, producing a list of transformed IR. These IRs are then lifted back into the Wasm modules. Finally, the generated modules are sequentially executed by the runtime. If new code passes are uncovered or the runtime crashes, the corresponding test case is added to the seed pool or the crash directory, respectively. Otherwise, the test case is discarded. We then illustrate the mutator design. The control flow mutators are dedicated to exploring various possibilities within both intra- and inter-procedural control flow. And it is worth noting here that Wasm implements structured control flow with block, loop, and if-else instruction, and the code execution is only allowed to be directed to the labels introduced by these instructions. This will add an extra layer of validity check on the control flow integrity and demand some sort of adjustment to the stack-invariant transformation. However, we will not go into depth here and instead focus on the design intent of our mutators. More details about this can be found in the paper. First, the recursive mutator is designed to create more deeply nested control structures, which has proven useful in previous studies. For example, it may wrap the original block structure into another loop structure. The branch target mutator is devised to modify the target label of branch instructions to execute different control flows. For example, it may alter the control flow from transferring to label 1 to transferring to label 2. Finally, the co-target mutator is relatively straightforward. It changes the target function of the function call instructions. The data flow mutators are specifically designed to alter the stack values manipulated by instructions, as well as the way by which these values are processed. The first mutator is interesting value mutator. In Wasm, immediate values are used for numerical computations, memory addressing, and other operations. The interesting value mutator adjusts immediate values to boundary values in the hope of triggering edge cases. For example, it could change the value 5 in i32.constant instruction to the largest unsigned 16-bit integer value. The operator mutator replaces one operator with another following the principle of stack-invariant transformation. In order to change the way stack values are manipulated. For instance, since both i32.add and i32.les instruction pop two values of i32 type and push one value of another i32 type, they can be interchanged flawlessly. Finally, the splicing mutator combines different parts of two seed inputs to produce more varied test cases, which has been broadly adopted in the domain of mutational fuzzing. The splicing mutator directly reflects our stack-invariant transformation concept, where one instruction sequence in seed A are replaced with another instruction sequence in seed B, as long as their type effects on the stack are compatible. At last, the skeleton-based generator enables the construction of code snippets that are rarely encountered in the seed corpus. However, as we mentioned earlier, Wasm runtimes enforce type checks on both the stack semantics and the control flow integrity, which are intricately interconnected. It is hard for the generation algorithm to combine distinct aspects of the Wasm standard while simultaneously satisfying the required validity checks. To solve this, the skeleton-based generator separates the generation of control flow skeleton from the creation of actual stack values. For example, given the target result type, I32, F32, F64, which is the type of values expected to be generated on the stack. The generator first plans the overall control flow structure and determines which part of the target result type each control structure is responsible for generating. Here, the generator may choose to use one block instruction for the generation of I32 type and one loop instruction for the generation of F32 and F64 type. And in each sub-control structure, we can generate control flow structures recursively until a predefined maximum depth is reached, enabling the creation of more complex control flows. And when the maximum recursive depth is reached, the generator begins filling in instructions that produce stack values of the desired types, which is similar to the Qi generation. For the example here, if we assume the maximum recursive depth is 1, the generator may generate an I32 dot reinterpret F32 instruction for the I32 type demanded by the first block structure. And this instruction requires one F32 value to be on the stack. Therefore, the generator may further generate a F32.constant instruction, which pushes a value of the required F32 type. And since this instruction requires no input stack values, the generation for the first block structure completes. And next, we present selected evaluation results here. For the research questions we aim to answer, can Waltzz surpass existing state-of-the-art fuzzers in terms of both code coverage and bug finding capacity? What is the contribution of each mutator to the performance of Waltzz? How effective is Waltzz at generating semantically valid inputs? And we choose the following baselines for comparison. The first two, FL++ and Red Queen, represent the state-of-the-art gray box fuzzers. The last three are Wasm-specific fuzzers. Wasm-Smith is a random Wasm model generator that is guaranteed to generate valid test cases. And Wasm fuzzer is a gray box fuzzer that employs structure-aware mutations to Wasm modules. The last, Replic, is a black box fuzzer that solely performs splicing mutations. For benchmarks, Wasm runtimes can be classified into web and non-web embeddings. And in the web embeddings, we select three widely used JS engines: SpiderMonkey, JavaScript Core, V8. And in the non-web embeddings, we choose 4 Wasm runtimes: Wasm Micro Runtime, Wasm 10, Wasm Interp, and Wasm 3. And to address research question 1, we run Waltzz and other state-of-the-art fuzzer on 7 Wasm runtimes over a period of 72 hours, and repeat the experiment 10 times to mitigate the randomness. For code coverage, we leverage the edge coverage provided by FL++'s collision-free instrumentation as a proxy. And the coverage result is presented in the left figure. For the bugs identified by the fuzzers, we manually deduplicate them using the stack traces provided by address synthesizer, and the bug result is presented in the right figure. Long story short, Waltzz surpasses existing state-of-the-art fuzzers by achieving 12.4% more code coverage and discovering 1.38 times more bugs than the nearest competitor. And Waltzz has uncovered 20 new bugs in total, which have all been verified, and 17 CVE IDs are assigned. To answer research question 2 and evaluate the effectiveness of different mutation methods, we modify Waltzz and add a counter for each method. These counters are incremented when the corresponding mutation methods generate an input that finds new code passes. And we conducted this experiment on 3 web embeddings over a 24-hour period and logged the counter values at 1-minute intervals. The following figure demonstrates the result. And according to the figure, we find that all mutation methods contribute to the effectiveness of Waltzz, and different targets potentially favor different mutators. As an example, the splicing mutator is particularly effective at finding new passes in the spider monkey, whereas it performs moderately on other targets. To tackle research question 3, we conducted a 24-hour evaluation of Waltzz on 3 web embeddings, during which we recorded the number of both valid and invalid inputs produced by our mutators and the generator. The figure below displays the validity rates. And as we can see, Waltzz is able to generate hundreds of thousands of valid inputs with a success rate of 100%. This is a result enforced by our Stack-Invariant transformation. And that's all. Thanks for your listening. If you have any questions, please feel free to contact me at this email address.